Hello, dear students. Welcome to the channel and welcome to the playlist in which we are discussing about the symmetrical, unsymmetrical faults and their analysis. In the very first video of the playlist, which was also the which was also the previous video of the series, in that we have discussed about the basics of um symmetrical faults. We saw what effect the transient will leave on transmission line, and we also saw the short circuit current and reactances of synchronous machine when it is not loaded. So we are taking this class in the continuation of previous class. So if you haven't seen the previous lecture, please go and check it. The link will be flashing on the I button on the top right hand side corner of your screens, so go and check it. And if you have already, so let's move on with today's topic. Today we are going to discuss about the analysis of short circuit of synchronous machine. So up till now we have seen how does the reactance will take play reactance will affect the operations of synchronous machine when it is not loaded. So this time let's talk about a fault a little. When a short circuit fault will occur at the terminals of synchronous generator, what will happen? The initial short circuit current will be limited by which reactance? The subtransient reactance. Remember, last time we divided my reactances in three part: subtransient, transient, and the steady state. So the subtransient will take care of this one. uh, so it will be the short circuit initial short circuit current will be limited by subtransient. After few cycles, it will be controlled by the transient reactance, right? And after that, the transient period will be over. After the completion of transient period, what will happen? The short circuit period uh, can be handled by your steady state reactance, right? Which will be the period will be called steady state period, and it will get settled in steady state. That's what happens, right? So the short circuit period can be divided in three period as well, just like we divided reactances. First will be subtransient period. You can see this in here. This is the subtransient period in which uh, only first few cycles are coming into the consideration, as you can see here, right? And in this time, initial time when the current is too high, so the current decay will also be very much rapid. As you can see, it is very rapid. It's um, it's uh, not close to steady state. After that, the second period will be the transient period. As you can see here, this the middle period is the transient period, and uh, this transient period will be relatively longer compared to my subtransient. And current will decrease here as well, but not at the rate as quick as the subtransient period. It will decay, but the decrement will be moderate, not too fast, not too slow. And finally, we will have the steady state period. In that, the decrement of current will be too slow, and at one point, it will be there will be no decrement, right? So it will be constant. So how do we calculate the values of this currents? Subtransient current. As you can see, we call the subtransient current I max double dash. Transient current is I max dash, and the steady state current is I max. So if you want the magnitude, you can say that subtransient period is having current magnitude of OC, transient is having current magnitude of OB, and steady state is having current magnitude of OA, right? So the formulas for subtransient current, transient current, and steady state current are as given as here. It will be Eg max divided by XD double dash. That will be for subtransient. For transient, we will have Eg max divided by XD dash. If you remember, XD double dash is the reactance related to sub-transient period or the sub-transient reactance. The XD dash is the transient reactance and XD is steady state reactance. So to find the transient current, you will take Eg max divided by XD dash, and for steady state current you will take Eg max divided by XD. Now what is Eg max? So it is nothing but Eg max is nothing but the value of your voltages or your supply voltages, right? Maximum voltage from um, one terminal to you can say your neutral, right? In the condition of no load, Eg max will be the maximum voltage from one terminal to neutral. And now the current is sinusoidal, as you say, as you saw over all the cycles. So in order to obtain the RMS value or the effective value of um, your voltage, what you will do, you will divide it by root 2, right? So to find the Eg, we divided Eg max by root 2 here, as you can see. Now what will be the sub-transient current in such case? When we divide it by root 2, the formula will change. Instead of Eg max, everywhere we will have Eg, right? So see here, for a sub-transient current here again, right? But this value will be RMS, right? Here we were calculating for maximum values for all three of them. See, maximum value, maximum value, but here we are calculating for only the RMS value. So uh, RMS value of sub-transient current will be Eg divided by XD double dash. The transient RMS value of current will be Eg divided by XD dash, and RMS steady state current will be Eg divided by XD, right? So these will be values of current, and that was the analysis of short circuit on a synchronous machine. Now we will see about the internal voltage of loaded machines under your transient conditions. So up till now we were watching for no load conditions. Now we will be seeing what will happen when your machine or synchronous machine is actually loaded, right? So we are considering that synchronous machine is loaded when short circuit is happening, short circuit fault is happening in my machine, and this has been indicated by this image. As you can see here, we are having a synchronous machine which is operating under steady state condition. You are having load current I0 or IO, you can call whatever you want, and terminal voltage is V0, as you can see here. We are having induced EMF, which is EG, and your reactance for direct axis is given as XD. Now whenever the short circuit will occur at the terminal of your machine, the short circuit current will start flowing through it, and because it is time dependent, it will change from sub-transient to transient, as we saw previously, right? So first will be sub-transient period, that then we will have transient period, and in the last we will be having uh, steady state period, right? So if you want to see this circuit model for transient or for transient or sub-transient, what will how the model will look like? It will look like exactly like this, but instead of this reactance, this is the reactance for steady state conditions. For transient conditions we will have XD dash, and for sub-transient condition we will have XD double dash. The rest of the things will remain as it is, except that one more change will take place, that your induced EMF EG, in case of sub-transient, your EMF will become EG double dash. If you are taking XD double dash as sub-transient reactance, then the sub-transient induced EMF will be EG double dash, and if you are taking your if you are taking your transient reactance XD dash, then the induced EMF on transient level will be EG dash, right? And how you will indicate the formula or how will you display that value of your EG? How will you determine the value of your EG dash and EG? So it will be same. Apply your KVL in this loop. You can find value of EG double dash. You can see it will be this voltage V0 plus I0 into XD double dash. In case of subtransient, it will be XD double dash, and your subtransient induced EMF will be EG double dash, as you can see in this formula. And as you can see in the very next formula, it is the formula for induced EMF in transient condition. EG dash will be equal to V0 plus J I0 XD dash, right? uh, After that, uh, we can do one thing, that in synchronous motor, as you know, that induced EMF and reactance are similar to the that of generator, right? But the direction of current will be reversed. So simply, in order to find the same values for uh, if this was for generator, if you want to find the same thing for motor, what we will do, for same fault, as for same short circuit fault, you are looking for short circuit voltage behind transient and your sub transient reactance for synchronous motor. So the formula will remain same. There will be a small change because in synchronous motor the induced EMF and reactances are similar to the generator, but because we are changing the sign, the current is flowing in the reverse direction. This sign, which was plus in the case of generator, will be minus sign, right? So for the case of motor, what will happen, your EM double dash will be V0 minus J I0 XD double dash. Again, XD double dash is same, your sub transient reactance, and XD dash is transient reactance. So value of transient EMF in the case of motor, EM dash will be V0 minus J I0 XD dash, right? So nothing new here, we just inverted the sign. Initially we had plus, now we will put minus, because in case of motor the direction of the current will be different than generator. So that was that for loaded conditions, and that was that from the perspective of induced EMF, right? The short circuit analysis of if you are doing for whole interconnector system, the synchronous generator and motor are replaced by their subtransient and transient circuit models, and all the other components of your network will not be changed, because those are passive elements, right? Those are passive elements of your system, so there will be no change in them. But because your synchronous machine, motor or generator, will be active components, so you need to change them. Now let's come to the short circuit calculations. So we want to find the value of current in the short circuit, and for that we will be required to make so many assumptions. So firstly, let's say you want to do analysis of symmetrical fault, right? So which quantities do we analyze, or do we consider while doing the analysis of symmetrical fault? So there will be first of all, there will be voltage at any point or at any bus in your power system. Secondly, we will have current in any branch of your system. And third, we will have reactance, which is necessary to limit your fault current to whatever the value you wish for, right? And now, how do we do this analysis? So the analysis is done in order to decide the rating of your circuit breaker, and also the current which is limiting your reactors, right? And precise calculation is not required, because the circuit breakers are manufactured in the standard sizes. As you know, your air circuit breaker or vacuum circuit breaker, whatever circuit breaker you take, you will have it in standard size. Like you will find circuit breaker of 250 MVA, 500 MVA, 750 MVA, right? 1000 kVA, 1000 MVA. And also the system impedance is also unknown. Like, it's not like completely unknown, but you don't exactly know what value it will hold. The most accurate value will not be there for the system impedance, right? So um, accurate calculation is virtually impossible because you don't have this system impedance value very precise. So when you don't have a precise value, what do? We make assumptions, right? So, and let me tell you, we will be making a lot of assumptions, right? We will be neglecting almost every other detail except for reactances. So let's see. First assumption is as compared to fault current, load current will be very negligible. So we will neglect the load current. Then the shunt capacitance of your transmission line will also be neglected, which we do in the most of the numericals, if you have seen the numericals in previous lectures as well. Third one, the shunt element in the transformer model will also be neglected, right? Because what do we do with transformers? We represent it in the reactance form, right? Reactance is in series, because the resistance of your transformer will be very low compared to its reactance. So uh, we basically ignore the resistance, and also shunt elements of transformer will also be neglected in here in this case. Then the resistances of your whole system will also be neglected. Only the inductive values will be considered, which means reactances, basically inductive reactances will be considered. And uh, what about transmission line, right? So as you already neglected the shunt capacitance, so you will be representing your transmission line by simply showing it as a series reactance. You can do that, right? So remember, I told you in the earlier told you earlier as well that we will be ignoring almost everything except for reactances. Then also the EMF of all the generators will be assumed to be equal, and particularly we will be including one angle zero in polar form. And what does that one angle zero means? It means the system voltage is as its nominal value, and uh, all of them are in the same phase. All of them are at starting from zero angle, right? So the selection of zero phase for one source is arbitrary, and it is convenient, right? In the calculation, it will be very convenient. You will not be needed to subtract this value, that value, right? It will be convenient. And by assuming all sources in phase and same magnitude, what you can do, you can neglect the pre-fault load current, right? Either ways, we neglected the pre-fault load current. Then the effect of DC component will be considered by using correlation factor. There is something called correlation factor. We will talk about it as we move further in the chapter. Now, these were the assumptions. Now, what will happen in the case of fault? So, let's first talk about the reactance of generator, right? Normally take it we normally take the reactances of generator as subtransient values. But if transient currents are also determined, then the transient reactances will be used. But the fault analysis is done by network reduction techniques. And if you have taken the circuit and network classes, you might remember Norton, Thevenin, right? Millman's. Those are your network reduction techniques. Now this three-phase symmetrical fault is the balanced nature of fault. Always remember, here we are only going to talk about the symmetrical faults. So uh, because we are talking about symmetrical faults, the chapter is all about symmetrical faults. So it will be balanced in the nature, and as the system is in balance, then only condition if you are applying it to one phase, then it will be equally applicable to remaining two phases as well, which means all the three phases will be facing the same conditions, right? If there are any. And the steps which are involved in three-phase symmetrical fault will in analysis will be six in total, as I've mentioned in this slide here. So firstly, what we will do, we will draw the single line diagram of the components, right? uh, we will include each and every component of my whole network. We will take its ratings and resistances, reactances. We will take everything in consideration of whatever component which we have drew. The second point is we will choose the common base or base kVA or MVA. You can pick whatever you want to pick. And we also know how to pick the value of base kVA or MVA. We discussed it about in the first lecture. Not first lecture, but in the playlist of basics of power systems, when we discussed about the per unit systems, we discussed about it, right? Third point is the we need to convert these single line diagrams to impedances or reactances, right? Basically you will be converting the single line diagram to impedance diagram or reactance diagram. We learned that as well previously, how to convert your single line diagram to reactance diagram or impedance diagram. After that, we will use the network reduction techniques which I've talked about a minute ago, and we will reduce this reactance diagram or impedance diagram using these techniques. You will it is up to you and the thing which you are doing, like because we are doing the short circuit calculations, we will be considering Thevenin's theorem. If you are doing something else, you will be needed to consider other theorems, and by doing that we will be keep the identity of my fault. In the next step, the fifth step, what we will do, we will find the reactances of the system, and we will find the reactances of system as seen from the point of view of fault, right? And after finding the reactances of my system, what we can do, we can simply calculate the fault current and fault MVA in per unit, right? And after your job is not done yet. Remember, whenever you convert your whenever you convert any of the quantity in per unit, you again also have to put it back in actual units as well. So after doing that, you have to convert per unit values to your actual values, right? And how do we do these calculations? So come here and see, this are the formulas. We don't follow the formula 4.1 4.4.1 and 4.4.2 very often, but we follow this formula. First we calculate the fault MVA. The formula is given here, you can see. We take base MVA divided by per unit equivalent into the MVA which is lagging, and once we find the fault MVA, we can find the fault current ISC by taking the division of base MVA divided by base kV. We multiply the base kV with root 3. Remember why? If you remember, mention it. Mention your answers in comment section. Let's see who remembers and who forgets it. And then we multiply it with your per unit value of short circuit current, right? Not per unit value, sorry, you will multiply it with the actual value of your short circuit current, because we are finding the per unit value of my fault current, right? So that's the formula for fault current and fault MVA, and that's pretty much it. Calculations from the short circuit perspective. Now if you are using ZBUS equivalent circuit, you can find the same you can find the value of your short circuit current as well. And what we will do, so when we talked about the network reduction techniques, particularly in Thevenin technique, that the Thevenin's equivalent circuit is very helpful for the symmetrical fault analysis, right? You must have seen in the circuit network. I'm not repeating what is it and how we can reduce my circuit because it will be too long and we don't have that much of time. But what we will do, we will basically cut off your cut off the values of your resistances, and you will form one resistance which will be equivalent to all those resistances, and then we will take the voltage across it, right? So the Thevenin's equivalent circuit will be very helpful for the symmetrical fault analysis, and the ZBUS matrix or ZBUS matrix elements can be used to construct your Thevenin equivalent circuit, the circuit which I was just talking about a minute ago, right? So you can find the voltage value between any pair of buses in your network. So we are going to do that. We are going to mention we are going to find the values of voltages between your K and J buses. As you can see here, J and K, we are having it here. So impedances are corresponding to the elements of ZBus are given here, as you can see here, ZKK, ZKJ, ZJJ, right? And all the pre-fault bus voltages will be same, will be VF, as you can see. Now the load current of the bus will be neglected. Remember, we did it in the calculation of synchronous machine in loaded condition as well, so we are going to do the same here. Then we will take the 2 points which are marked by A and A as A here, and we will state that both of them are at same potential, because basically the potential which is going through here is VF, right? So both of them are in at same potential, and because of that we can join them together to obtain the equivalent circuit. So instead of separating, putting them here, we joined them here at point A, as you can see in the second circuit. Now what we will do, you can see there is a switch I have put over the bus K. So in the case when the switch is opened, there will be no short circuit current will be there will be no flow of short circuit current here, and or any branch of your network, right? Because it is open circuited. But at the moment when I close the circuit or close the switch, this switch, we are closing it over here, what will happen, the current will start to flow in the circuit towards the bus K, right? Because we are closing it here, so current will come towards bus K, and uh, what will be the value of that current? So you can see on this what is the value of this current. As you can see, IF double dash, what is the voltage was VF, and what is the impedance is ZKK. So the value of current will be VF divided by ZKK, and because of that, what will happen, it will induce the voltage drop uh, in the direction of my J bus, this bus as well. And what will be the value of it, right? What will be the value of it, the voltage drop across my J bus? It will be, see here, we are having VF here, so VF into ZJK, because half current got here, ZKK. So the current the impedance which will be associated with my jth bus will be ZJJ, so it will be VF into ZJK divided by ZKK, right? And this way, by substituting the appropriate values for impedances in the equivalent circuit of my Z bus, what we can do, the bus voltage of the system before and after the occurrence of fault can be calculated, And if my switch is closed in the second case, as you can see, uh, it is reflecting the voltage bus J with respect to the reference, while the fault is on bus K, right? And because of that, what will happen if three-phase short circuit fault will occur at kth bus for any large system? We can calculate the fault current and voltage at any unfaulted buses by inserting the proper impedance value in elementary circuits, right? Which circuits? This circuit. So we can neutralize it. Next, we are going to see the selection of circuit breakers, but not in this lecture. We will be seeing it in the next lecture. We will keep this lecture till here. If you have any doubts, any queries regarding today's lecture or any previous lecture, please feel free to mention it in the comment section below. I will try to address them as quick as possible and as soon as possible. Except that if you have any feedbacks related to channel or related to the pacing of the lectures, related to any other thing, please feel free to drop them down in the comment section below. I will try to improve them as much as I can and as quick as I can. So until next time, thank you very much for listening. I will be seeing you in the next lecture. Goodbye.